Hi, I'm Tianxiao. I'm very happy to talk about our paper, Aggregating Text Autoencoders, Latent Representation Guidance while Denoising. This is joint work with Jonas Mueller, Regina Barzilay, and Tommi Jaakkola. Autoencoders have become popular tools for advancing controllable text generation. They have an encoder and decoder network, such as LSTM or transformer, to map between sentences and vectors in a latent space. These models offer an attractive, continuous approach to manipulating sentences while modifying their latent representation. For example, we can encode the sentence, "This talk is awesome," into its latent representation, add a tense vector, and then decode it back to get the sentence, "This talk was awesome." Similarly, we may subtract a sentiment vector and change "This talk is awesome" to "This talk is awful." The success of such manipulations rests heavily on the geometry of the latent space vectors, namely, which mapping between sentences and latent vectors will the model learn. Say we have 4 sentences: "This talk is awesome," "This talk was awesome," "It's sunny today," "It was sunny yesterday." Will the model map "This talk is awesome" to the latent space close to "This talk was awesome" and far from the other 2 sentences? We discovered that without additional guidance, fortuitous geometry that captures sentence semantics is unlikely to arise, shedding light on challenges faced by existing models. The figure on the right depicts the representations learned by the adversarial autoencoder when mapping clustered sequences into R2 space, where different clusters are mixed together in the latent space. We'll explain this experiment in more detail later. In such cases of failure to maintain a latent geometry coherent with the data structure, even minimum latent space manipulations can yield random, unpredictable changes in the resulting text. Like "This talk is awesome" after encoding a small move in the latent space and decoding becomes an irrelevant sentence, "It was sunny yesterday." In this work, we focus on the adversarial autoencoder, or AAE for short. It involves an encoder E mapping from sentence X to latent vector Z, a decoder G that generates sentences from latent vectors, and a discriminator D that tries to distinguish between latent representations and samples from a given prior PZ, usually Gaussian. E, G, and D are trained jointly with a min-max objective. E, G minimize the loss of reconstructing X from its latent representation Z, and min will maximize the loss of D such that the latent encodings are indistinguishable from the prior samples. Once the model is trained, we can generate new data by first sampling Z from PZ and then mapping it to the data space. We extend AAE by introducing a perturbation process C that stochastically maps X to nearby tilde X. Here, we randomly drop each word with probability P. So "This talk is awesome" may remain unchanged or be perturbed into "This talk is awesome," "This talk is awesome," "This talk is," "This awesome," and so on. We ask the model to reconstruct X from tilde X. As we shall see, this implicitly encourages the model to map similar sequences to similar representations without requiring any additional training objectives. Our model combines the denoising technique with AAE, named DAAE. Denoising has previously been applied to images to learn robust representations. Here, we show that it is particularly useful for discrete text modeling with powerful sequence networks because it induces preservation of data structure in the latent space. Let's first study the latent space geometry of AAE and DAAE through a toy experiment. We generate synthetic data of binary sequences stemming from 5 underlying clusters with 100 sequences sampled from each. Sequences from the same cluster typically have many more elements in common than those from different clusters. We train AAE and DAAE models with a latent dimension of 2. Both models can achieve perfect reconstruction at test time when perturbation is disabled for DAAE, and meanwhile keep the adversarial loss close to its maximum. The learned representations are plotted and colored accordingly by cluster identity. From the left, we see that the AAE latent space mixes different clusters together. This is because for discrete objects like sequences, neural networks have the capacity that even if you change one element, you can map it to a distant representation. On the right, the DAAE latent space closely captures the underlying cluster structure in the data. By simply introducing local input perturbations, we can ensure that similar sequences have similar representations in the trained autoencoder. We provide theoretical explanations for this phenomenon by formally analyzing which type of XZ mappings will be learned by AAE and DAAE respectively to achieve global optimality of their training objectives. Our first theorem shows that with high-capacity encoder-decoder networks, any assignment between training examples x1 to xn and latent points z1 to zn can achieve the same optimal value under the AAE objective. Therefore, AAE offers no preference over XZ couplings, and a random mapping, such as the one shown in the figure that maps close X to distant Z, is equally good as any other matching. Our second theorem considers DAAE in a simple scenario with only 4 examples. Given C perturbs X to its neighbor, we can prove that the optimal assignment is to map close pairs of X to close pairs of Z. At a high level, this is because a close pair X1, X2s encoding Z1 and Z2 have shared goals that they both need to reconstruct X1 and X2. Thus, putting them close to each other in the latent space can help reduce the reconstruction loss. We next generalize this basic 4-point scenario to consider n examples of X that are clustered. We present a sketch of the theorem here to illustrate the idea. Please refer to our paper for the formal theorem. So suppose x1 to xn are divided into n over k clusters of equal size k. Let the perturbation process C be uniform within clusters. The DAAE objective is best achieved when examples in the same cluster are mapped to the latent space in a manner that is well separated from encodings of other clusters. In other words, by preserving the input space cluster structure, DAAE can achieve better objective values and thus is incentivized to learn such mappings. This explains our finding in the previous toy experiment. Natural language also exhibits cluster structure based on topics and authorship, but it also has more complex syntactic and semantic structure. Let's now study the performance of DAAE on real text data. We compare it with AAE, latent noising AAE, or LAAE for short, and beta VAE. Both LAAE and beta VAE introduce Gaussian perturbations in the latent space, whereas DAAE introduce input perturbations on the sentence space. We evaluate various autoencoder models in terms of their neighborhood preservation property, their generation and reconstruction capacities, and their application to style transfer and sentence interpolation. We show results of the Yelp reviews dataset in this video. For more baselines, human evaluation, and results on the Yahoo Answers dataset, please check our paper. We begin by studying the nearest neighbors of test sentences found by AAE and DAAE based on Euclidean distance in the latent space. For source sentence, my waitress Caddy was fantastic, attentive, and personable. The nearest neighbors based on AAE representation are my cashier did not smile, barely said hello. The service is fantastic, the food is great, which are not really relevant to the source sentence. In contrast, the nearest neighbors based on the DAAE representation are the manager Linda was very, very attentive and personable. Stylist Brenda was very friendly, attentive, and professional. The manager was also super nice and personable. This shows that the DAAE latent space is structured based on keywords such as attentive and personable, and tends to group sentences with similar semantics close to each other. On the right, we quantitatively measure that in the test set, for each sentence's 10 nearest neighbors in terms of normalized added distance, how many of them lie among the k nearest neighbors in the latent space? DAAE, indicated by the red line, consistently gives the highest recall rate for different k, about 2 times that of AAE, indicating that its latent space best preserves text similarity. We next evaluate different models in terms of their generation quality and reconstruction accuracy. Only when the model that both generates high-quality sentences and learns useful representations that capture significant data content, we can successfully manipulate sentences by modifying their latent representation. We compute the BLEU score between the input and reconstructed sentences to measure reconstruction accuracy. To measure quality, we use a pre-trained language model and evaluate the perplexity of generated text. We plot reconstruction BLEU, higher is better, versus perplexity, lower is better. The dotted line marks the perplexity of real data. The lower right corner indicates an ideal situation with perfect reconstruction and the perplexity close to real data. We vary the KL coefficient beta of beta VAE to get the spectrum of its generation-reconstruction trade-off. A standard VAE with beta equal to 1 completely collapses and ignores the latent variable, resulting in a reconstruction BLEU close to 0. As beta decreases, the reconstruction BLEU increases with the cost of high perplexity. AAE achieves near perfect reconstruction, but the generated sentences are of poor quality, indicating by its high perplexity. Introducing latent noises into AAE provides a model with a trade-off curve similar to beta VAE. Finally, varying the word drop probability P, our model DAAE offers a trade-off curve strictly superior to other models. By adding input perturbations, we can constrain the model to maintain coherence between neighboring inputs in an end-to-end fashion. The gray box indicates hyperparameters we finalize for respective models to ensure that they encode enough data content. Now let's apply the models to unsupervised text style transfer. After training an autoencoder, we take 100 sentences of one style, encode them, and compute the mean representation. We do the same thing for sentences of another style, and then use the difference between the mean representations as a style vector v. Now, we can, given a sentence, we can change its style by adding or subtracting v in the latent space. Note that we do not require any style labels during training, and thus our model can easily scale up to train one large model on unlabeled corpora, and then applying for transferring various styles. We first test models to transfer between past and present tense. We compute the transfer accuracy, that whether the output sentence has the proper tense, and the output blue with the input, and the perplexity evaluated by a language model. Ideally, we should achieve 100% accuracy, a fairly high blue score, that the sentence is faithful to but not exactly the same as the source, and a perplexity close to original data perplexity. We see that AAE has the highest blue but the lowest accuracy, indicating that it usually does not change the source sentence. DAAE achieves the highest accuracy, the lowest perplexity, and the relatively high blue score, indicating that its generated outputs are of proper tense and high quality, while remaining faithful to the source sentence. Here's an example. The input sentence is, "The staff is rude and the doctor does not spend time with you." Beta VAE and LAE generates inappropriate outputs, like "the doctor did not spend time with your attitude," or "the doctor is even for another of her entertained," which doesn't make sense. AAE changes is to was, but fails to change does to its past tense. Only DAAE generates the correct output. The staff was rude and the doctor did not make time with you. Applying DAAE to sentiment transfer, we observe that scaling V to 1.5 times V or 2 times V, the resulting sentences get more and more positive or negative. For example, changing "the food is entirely tasteless and slimy" to positive. The results are "the food is tremendous and fresh" to "the food is sensational and fresh" to "the food is gigantic." Or changing relaxed to negative, we get stressed and annoyed successively. Quantitatively, as the scaling factor increases, the accuracy increases, but the output is less similar to the input and the perplexity is higher. On balance, DAA with 1.5 times V is comparable to previous models trained with sentiment labels. We also study sentence interpolation while traversing the latent space of text autoencoders. Given two sentences, we encode them to Z1, Z2, and decode from T times Z1 plus 1 minus T times Z2. Ideally, we should get fluent sentences with gradual semantic change. Here's an example, interpolating between "it's so much better than the other Chinese food places in this area" and "better than other places." AAE produces abrupt intermediate sentences, "better, much better," or repeats "better than other places." DAA, in contrast, produces more coherent and natural interpolations, from "it's so much better" to "it's much better" to "better than the other Chinese food," better than the other Chinese places in this area, better than the other places in Charlotte, until "better than other places." The sentences are changing gradually while retaining the topic and the syntactic continuity. In conclusion, the first point to take away is that simply minimizing the divergence between data and model distributions does not ensure that the data structure is preserved in the latent space. Second, denoising can greatly improve the text representations. We provide a theoretical explanation for this phenomenon by analyzing the latent space geometry arising from input perturbations. Our results might also help explain the success of BERT, whose mask language modeling objective is similar to a denoising autoencoder. Finally, DAAE best preserves sequence neighborhood, provides superior generation-reconstruction trade-off, and enables zero-shot style transfer. In future work, we can explore better or task-specific text perturbations beyond the basic random word deletion. We can study other properties of latent space geometry, such as the linearity we find in style transfer. We could provide finer control over text generation using autoencoder models. For instance, we can simultaneously modify multiple attributes of the sentence, or simplifying or expanding the sentence, and mixing sentences from different sources. Our code and data are available on GitHub. Welcome to try and play with it. Thank you.